Welcome back to ECE 501B. Today, homework number 8 is due. I think that's due at 11:59 p.m. If you haven't submitted it here, you can put it into the Dropbox up until that point. Your project is due on the 8th of December, which isn't too long away, as our final exam is not very far away either. It's 2 weeks from this coming Monday on the 16th, and it will be held in this room from 6 to 8 p.m. and it will be comprehensive. And hopefully we will have more than Chapter 7 on the final exam. Hopefully we will complete Chapter 7. This is the last result in Chapter 7, the singular value decomposition theorem, Theorem 746. Maybe we could feel comforted in the fact that we've looked at 46 different things in Chapter 7, potentially. But then I want to walk through a singular value decomposition matrix example. And I'll try to go quickly through that in terms of writing down all the numbers, but I want you to kind of start to get a feel for what the singular value decomposition allows us, or the power that it provides for us, and in particular, it identifies or produces basis vectors for the 4 fundamental subspaces of any linear map A. And I'll look at a linear map A that's not square, that's not an operator. It's now mapping between, now I don't remember, I think it's a from a 4 space into a 3 space in R4 to R3. Then hopefully we will get into chapters 8 and 9, which really what we will extract from chapter 8 and 9 are these ideas of generalized eigenvectors. We really haven't talked about that yet. We've avoided that issue, but if a matrix cannot be diagonalized, you don't have enough eigenvectors, and you have to create some new vectors, and those are called generalized eigenvectors, to allow you to almost diagonalize a matrix or put it into, let's say, a Jordan form representation. And that's what we will sort of extract down of chapters 8 and 9. Chapter 10, we'll get into roughly some other things with respect to, we'll finally get into determinants, which is typically where you start in a linear algebra course when you're doing just the matrix manipulation. We're finishing with determinants and trace, etc. Some of those concepts will now be available to us. Just to get us thinking again about what we had talked about, and in particular singular values, this is the example that we ended the class with last time, but I want you to sort of get back up to speed with where we were. It's a linear map that takes this 4-dimensional vector into another 4-dimensional vector in this particular way. We can pretty easily identify the matrix representation of that linear map. And by looking at the fact that that matrix representation is lower triangular, the eigenvalues are staring at us on the diagonal. We really only have 2 distinct eigenvalues, and that's where this generalized eigenvectors and eigenvectors come into play, is when we have repeated eigenvalues. In this case, we have 0 repeated 3 times and an eigenvalue at -3 for that particular linear map. We want to sort of compare that or contrast that with this notion of singular values. Singular values tells you how you expand or scale a vector through a linear map. It's not necessarily the same as these eigenvalues. We can, though, in this particular example, look at the adjoint. In this case, it's simply the matrix representation is going to be just the transpose of what I'm calling A for the matrix representation of T. So we simply flip things across the diagonal. Then if we look at this product of A transpose A, we see that, oh, for the first row, just scale the second row in A by a factor of 3. That's A transpose A. Scale for the second row in A transpose A, scale the third row by 2, where the third row is 0, 2, 0, 0, and that's going to produce this 0, 4, 0, 0. Doing that same process, we can now see that the eigenvalues of A transpose A are right there staring at us, 9, 4, 0, and 9. 9 is repeated. We've then defined these new concepts called singular values to be associated with the positive square roots of the eigenvalues of this matrix adjoint of t, t, which in this real number case ends up being 3, 3, 2, and 0. And we could contrast that with these eigenvalues of 0, minus 3. But that particular linear map is not invertible because we have an eigenvalue at 0, which we'll learn about when we start dealing in chapter 10, or we have a singular value of 0, so we're losing rank. We're not full rank in that map. If we took a 4-dimensional vector into another 4-dimensional vector, there is a vector that lies in the null space. We have a non-trivial null space for that particular map. That's sort of the concepts or ideas that are being played with just from that information. Let's now pick up with that. Now that we kind of remember what we're thinking about, we now have created these new items, singular values, that tell us how we're scaling vectors through these maps. Let's now decompose these maps using those scaling factors in addition to the rotation capability that we know we can do with isometries. And that leads us to the singular value decomposition. So here what I want to do is start with that, the singular value decomposition, or the singular values, lead to a particularly useful decomposition of any operator. And in fact, that particular decomposition is called the singular value decomposition, and a lot of times we will just simply say SVD for the singular value decomposition. That particular decomposition is prominent enough to get its own theorem. So theorem 746 is the singular value decomposition theorem. Here is what it tells us. Suppose that we now have this linear operator, T, on this vector space V, and suppose that we know what its singular values are, and we know how to compute those. We just showed an example of that. Suppose we have this linear operator T with singular values let's say S sub 1, S sub 2, up to S sub n. Associated with those singular values, there exists orthonormal bases. 2 of those, let's call one E1 through E sub n, and another one f1 through f sub n, two different orthonormal bases on our vector space V, such that we can re-express or decompose this operator T in the following way. The first singular value, S sub 1, is going to be scaled by V E1's inner product in the direction of F1, plus S sub 2 times the inner product of the vector V, any vector V, inner product in E2, and that now tells us sort of how V is aligned with these different E's, these different orthonormal basis vectors, and then we basically remap that through another basis vector. This S1 VE1, that's simply a scalar. S sub 2 inner product VE2, that's a scalar, and we're scaling these basis vectors F1 through F sub n, and we can keep doing that down to S sub n VE to the n F sub n. And that can be done for all vectors V in our vector space capital V. That's the decomposition. That's our singular value decomposition. The operator has some scaling based or given by the singular values, S1, S2 through Sn. We have two bases, and this will make more sense, I think, when we go through the proof of this. But we now have two different bases. First, we say, how does V sort of align with one of the basis vectors? And we could think of these E's sort of influencing the input into our operator. So we say, how does V align with the E's? And if that's a big value, this inner product will be big. And then we'll redistribute that information or remap that information through another set of vectors, orthonormal vectors, F1 through F sub n. Let's now prove this, and it will hopefully help illustrate where these ideas are coming from, or where this decomposition is coming from. First, if you go back and look at corollary 714, that actually allows us to make the following. Following statement. From corollary 714, there is a basis say E1, E2, E sub n, such that we can find, the eigenvalues and eigenvectors associated with the positive square root of T dagger T. Meaning the positive square root of T dagger T, that's now a positive matrix and self-adjoint. It now has a orthonormal basis set of vectors that are eigenvectors, and we can now say that that's E sub I is equal to lambda, oops, I'm not doing the right notation. I want to now call these the S sub I's E sub I. That we can get from corollary 714, and the fact that this positive, that we now have an operator that's the positive square root of something. So it's now self-adjoint, and now we have an n-dimensional set of orthonormal basis vectors. E's is what we're going to call those, and they have eigenvalues S sub I, where these S sub I's are really, the other thing that we're calling them are singular values of this linear map T. But we know that this can be found, these E sub 1 through E sub n. Once we have that, then given any vector V, we can decompose that vector V in terms of this orthonormal set of basis vectors, e sub 1 through e sub n. Meaning now we can always write any vector v as ve1 scaling e1 plus ve sub 2 scaling e2, etc., all the way to ve sub n scaling e sub n. We know we can decompose any vector that way in these different directions created by this orthonormal basis set, E1 through En. That should be okay. That we should feel warm and fuzzy with, that particular line. But now that we have this relationship for V, let's now manipulate that, or basically introduce what we need to essentially create T times V. So the first thing that we'll do is let's now not change this, but we'll change it, meaning let's multiply by 1, or let's multiply both sides by the same thing, where that same thing is the positive square root of T dagger T. On the left then, so now let's apply the positive square root of T dagger T of that equation. Meaning we now have the positive square root of T dagger T times V on the left. But then what happens when we hit all of these terms with the positive square root of T dagger T? Then whenever we hit E1, it's really equivalent to S1 E1, that positive square root of T dagger T. Because these are orthonormal basis vectors, we only have to worry about each one sort of separately. So when we hit E1, we're just going to really, when that's hit by this square root of T dagger T, this was a scalar, this VE1, that can be slid around, and when we hit E1 with square root of T dagger T, that's really just S1 E1. Is that okay? Meaning now we can rewrite the right-hand side as S1 VE1 E1 plus S sub 2 VE2 E2 all the way down to Sn VEn En. And we're almost to our linear map T. We would be there based on our polar decomposition if we simply operated on the left of both of these sides again by our isometry S. Isometry S times the positive square root of T dagger T gives us our T by construction of what we learned with our polar decomposition. And that's what we'll do now. And we have seen that there is an isometry, let's say S, that's also a linear operator on this same vector space, such that T is equal to S positive square root of T dagger T. Knowing that, now let's apply S to both sides of that last equality. So apply S to each side. And now we have on the left, we have S times this positive square root of T dagger T V equaling S times S1 V E1 E1 plus Sn V En En. But on the right-hand side, that S1 inner product is just a scalar. So let's factor that through the S, or push the S all the way up against the E's. Meaning, let's now rewrite that as S1 inner product of VE1 SE1 plus, and that keeps going, Sn V En SEN. We're almost there. What do we know about isometries? We know that they can basically rotate one orthonormal basis set into another one. And that's where the new orthonormal basis set's going to come from, the F's. I'm going to call SE1 F1. I'm going to call SE sub n Fn, because S is just rotating these orthonormal basis into another set of orthonormal basis. Let me now just say, let's define, or now choose, these F1, F2, F sub n such that F or S E sub I is equal to F sub I for all I equal 1 to n, or F sub I is equal to S E sub I, whichever way you want to write it. That now allows us to write down this piece right here is just T. So now we have TV is equal to S1 V E1 F1 and so on down to Sn V En Fn. And that's what we said our singular value decomposition was, is this expression. So let's now make some comments based on that particular result, that theorem. We now have two sets of basis vectors, E1 and F1, on the same vector space. And they're basically manipulating input to output, and we're scaling via these singular values, S1 through Sn. So the singular values sort of tell us how we expand or contract, and the E's and the F's tell us how we pull that information in from a vector, and F's pushing it out in a new direction. But they all combine to give us this linear map, capital T. Here are some comments that we can now make, or we could say that it's almost impossible to brag on this too much, or to say too much about this result. Has anyone seen the singular value decomposition before? No? Okay, well, boy, hold on to your hats. Some of you have, but it's very powerful, and it's a really strong numerical technique. So let's now make some comments. One I've just already been talking about is that it shows action of any operator, or it shows the action of any operator can be written in this decomposed way. One is we have this decomposition in one basis. By that, we're basically taking these projections of these inner products with V and the E sub i's, So that gives us sort of how the vector that we're introducing or inputting into this linear operator, how it's being felt by the linear operator by these inner products. If it's a strong feeling, then this inner product piece will be big. If it's weak, then maybe it's going to be close to 0. If it's in the null space, then that inner product would be 0 if it was in the null space of that linear map, the vector v that you're applying to that linear operator. So we're decomposing, or we have a decomposition in one basis, which is the e's. Then for each of these, VE1, VE2, we scale them by the appropriate singular value. So do we then have this scaling of each component by the S sub i's. And finally then, we redirect that number, that scalar, in the direction of F1, F2, etc. So we now do this recomposition. We sort of now put it back into the space that it's returning to. We recompose or recomposition in a different basis, which are these F sub j's. It's actually a little bit weird, isn't it? Because when we have been thinking about operators, typically we just have one basis set. Now we have two. So that's kind of the weird part. We normally only use one basis with an operator. Here we actually have the two, the E's and the F's. Here we have, and we could think of those as an input basis and an output basis. So this is just like with a matrix representation of a map. We sort of have the input space and the output space. So this is just like with the matrix representation of any linear map. And we could actually sort of comment on what that looks like when we represent it in those two bases. So what's the matrix representation of this linear map T look like with respect to the E's and the F's? And that notation has already been introduced in the book. But this you could think of as the input basis, and there's the output. So what does this matrix representation of T with respect to E's and F's look like? That's actually going to look like a diagonal matrix with the S's on the diagonal. So we have S1, S2, S to the N, and a lot of times these singular values are ordered from biggest to smallest in absolute value, and some of these might be 0 if your linear map is singular. Here you could think of your output basis on the row side and your input basis operating on these columns. So E1 gets scaled by S1 and pushed out via F1 is one way to sort of think of it. So it looks like this diagonal with the weighting on those two basis vectors, E1, F1, etc., being the singular values. In fact, we can apply the SVD, the singular value decomposition, not just to operators, but to generic linear maps. They don't have to be square in terms of operators. So in fact, we can apply the singular value decomposition to generic linear maps, which we might represent as T being a element of this linear map from V to W. Which allows us then to really sort of think about this in a sense of a generalization of eigenvalue eigenvector analysis. This is now a generalization of, let me just say, eigenanalysis to maps, because linear maps generically don't have eigenvalues, do they? Because in a matrix sense, they're not square, and we can't talk about eigenvalues and eigenvectors with non-square matrices. So this is a generalization of eigenanalysis to maps, or in terms of their representation, rectangular matrices, non-square maps. Just as a repeat then, no eigenvalues of a generic map really exist, but if we now are starting to talk about this guy, this positive square root of T dagger T, that's a positive matrix, it's square, and it does have eigenvalues, and that's what we introduced in order to try to find singular values. We're taking these positive square roots of these T dagger T eigenvalues. So this guy is square, and because of that, it does possess or have eigenvalues. The fourth comment, I said we couldn't say enough. I only have 30 of these, so hopefully you have enough Gatorade or something so that your hand doesn't cramp from writing. No, this is the last one, and then we'll go through an example. So 4 is can also view this SVD as a matrix factorization. And that matrix factorization is typically written as T, if I can sort of be bold enough to say T is now going to be a matrix. That's now U sigma V transpose. And MATLAB actually allows you to do this rather easily. If you now, I'll probably get it wrong, but if you did something, you can always do help SVD, and I think that's the functional form of it, but you could say something like U sigma V is equal to SVD of T, and it would then give you these three matrices, U, sigma, and V, where V is the transpose. So let's look at a matrix example of this, sort of just sit back and look at what the numbers are, and I'll try to quickly put this on the screen. It may take a while, but hopefully you'll start to see what can and can't, well, what can be done with singular value decomposition numerically. Here's an example then of SVD of a particular matrix. Suppose somebody gives you this matrix A. First column is 1, 0, 1. The next column is minus 1, 1, 0. The third column is 0, 1, 1. And the last column is 1, 1, 2. And this is now an element of a 3 by 4. Meaning our domain of A is R4. That's where we're pulling the inputs from. The codomain is not as big dimensionally. It's 3. We're mapping into a 3-dimensional space. This is now what you could think of as the output of that map, of that linear map or that matrix. And if you look at this, maybe not, it's clear the rank. Have you heard of the rank of a matrix, or how many linearly independent columns or how many linearly independent rows, those are equal, does this matrix possess? So you're looking to see, is there some dependency among my columns, or is there dependency among the rows? If there's 2 linearly independent columns, there's only 2 linearly independent rows. Those are always equal, the number of linearly independent columns and the number of linearly independent rows. So you know this particular map, because just of its dimensions, 3 by 4, what do you know about it? Is it injective, surjective? Do you remember all those concepts? Do we have a non-trivial null space? Is that clear just from the dimensions? I'm going from a bigger dimension to a smaller dimension. So just from that fact, I know that I have to have a non-zero null space, a non-trivial null space. And in fact, I cook this up to where I actually have, I'm losing rank in not only the input sense, but also I'm not mapping into a 3-dimensional full room. I'm maybe just sticking with the floor. I'm just staying with a 2-dimensional space. These 4 columns, there's only 2 of those 4 that are linearly independent. And you can kind of see that the way, just add the first 2 and you get the third column. And then if you add the third column to the first column, you'll get the fourth column. So these are just linear combinations of the first 2 columns. So this matrix has a rank of 2. So I'm going to basically only have, and you can get the rank by looking at your non-zero singular values. I'm just going to have 2 non-zero singular values for this matrix A. So let's now look at what we have for this particular matrix A. First, we can talk about A's decomposition as U sigma V transpose. U, the columns of U actually form orthonormal vector, or they are orthonormal vectors, and they form a basis for the codomain, R3. So this is now a set of orthonormal vectors. That's U. The columns in V are similar in terms of they are also orthonormal vectors, but they now span our domain, a 4-dimensional space. And sigma that's actually dimensionally the same as A. So it's now 3 by 4, but the elements on the diagonal, it's only a diagonal matrix. And the elements on the diagonal are the singular values of the matrix A. So this is now, it's not a square matrix necessarily, but the diagonal entries on that matrix, the 1, 1, the 2, 2, the 3, 3, those are the singular values of the matrix A. That's where you will find those. So can I sort of be maybe not accurate, but I'll just say this is sort of a diagonal matrix of singular values. With that decomposition, U as a matrix in this example is 3 by 3. Sigma is 3 by 4, and V is 4 by 4. Now, how do we find the singular values based on what we've done so far in this class? We would take T dagger T, find their eigenvalues, and take the positive square roots of those, right? So if we looked at the eigenvalues of T dagger T and took the positive square roots of those are the eigenvalues those are the singular values of T. So we could, with this matrix A, we could compute A transpose A and find the eigenvalues and take the positive square roots of those to get our eigenvalues. Maybe I should do that now. Maybe that's the better place to do that. If we looked at A dagger A, since we're dealing with real matrices, we don't need to worry about the conjugate, do we? This is now A transpose, A transpose A, which actually ends up being 2 minus 1, 1, 3, minus 1, 2, 1, 0, 1, 1, 2, 3, and 3, 0, 3, 6. Is it obvious what the eigenvalues of that are? No. But if you find those, the eigenvalues of A transpose A are actually 3, 9, 0, and 0. So our singular values of A in our example are going to be the positive square roots of these eigenvalues of A transpose A, and that then says that these will be 3, square root of 3, 0, and 0. Those are our singular values, or really, I should maybe say we only really have, in this case, one of those zeros. It kind of depends on how, I guess, you expand that. But in this case, the most you can really have is the smallest dimension of your matrix A, and that was 3. It was 3 by 4. So now that we know the singular values, now we can build up this sigma matrix. We said it was diagonal. On one of those, we have the biggest one, 3. The next one is the square root of 3, and then we have a 0. And what's the size of this matrix? We said it was 3 by 4, didn't we? So if we really wanted to partition this matrix, we could think of this as some smaller non-zero diagonal matrix, sigma bar, with non-zero or with zero submatrices surrounding it. And in this case, the sigma bar is 2 by 2. This matrix is 3 by 4, where our sigma bar is this 300 square root of 3. Those are now our singular values. If we build this up or put it to MATLAB, we would then get a U matrix that's 3 by 3. And the U matrix is going to be minus 0.4082, minus 0.4082, minus 0.8165, 0.7071, minus 0.70710. And then we actually want to partition it compatibly with the sigma matrix, and the last column is 0.574, 0.5774, 0.5774, and minus 0.5774. And the way that I've partitioned this, U sub 1 is a matrix that has 3 rows and 2 columns. U sub 2, 3 rows and 1 column. And that's compatibly partitioned with sigma. I'm multiplying U times sigma, and if I look at this 3 rows or 3 columns in the top row, this row needs to be compatible with the big sigma, which had 3 rows. And if I keep doing that, then I should see that this last column of 0.58 is going to be getting scaled by that 0 row in the sigma matrix. Now, if I look at this, how many non-zero eigenvalue or singular values do I have for this map A? I had 2 non-zero singular values. So I have 2 linearly independent columns or 2 linearly independent rows of A. Now, if I have 2 linearly independent columns, I have to have 2 vectors that are going to span that 2-dimensional space. So the range space of A is going to be spanned by the columns in this U sub 1 submatrix. That's the 2-dimensional, or the 2 columns in the total U that are going to span the same thing as the range space of A. So now I'm basically showing you where these 4 fundamental subspaces are coming from in this decomposition. The span of U sub 1 is the span of A, which is really just the range space of A. But what did I say about the columns of U? They were orthonormal. So the third column is orthogonal to the front 2. So it must be in an orthogonal complement to the columns of U sub 2, which means that if I wanted a basis for the orthogonal complement to the range space of A, I have it in that column, in this case just 1, the columns of U sub 2. So now that I've identified my partition in the matrix U, I can immediately find basis vectors, orthonormal basis vectors, for 2 of my fundamental subspaces associated with the linear map A. One of the fundamental subspaces is the range of A. Where can I get to if I operate on 4-dimensional vectors with this matrix A? The only place I can get to is the span or the range of A, and that's spanned by these two columns of U1, and now I have an orthonormal basis for that spanning set. If I need to get to the orthogonal complement to the range of A, or a range of A perp, then I need another orthogonal direction, and U sub 2 provides that for me in this decomposition. I know this is kind of maybe a lot, but this is pretty powerful stuff. So now let's look at what we have on the other side. This is sort of the output side. This is where we get to through the map. This is where we end up, is the range of A or its orthogonal complement, range of A perp. What about the V's? If we look at V, here is our decomposition. A is equal to U sigma V transpose. V, if we did the singular value decomposition in MATLAB, it's now a 4x4 matrix. It's now going to be minus 0.4082, 0, minus 0.4082, minus 0.8165, 0.4082, minus 0.8165, minus 0.4082, 0, and again, we have two non-singular singular values, so we can partition this 4x4 matrix into two sets of columns, the first set being 2 wide, the others are whatever is remaining, and in this case it's 4 minus 2 or 2 also. So this case, or this set now is minus 0.707, 1, minus 0.5571, 0.4082, 0.1494, and finally minus 0.4082, 0.1494, minus 0.7071, and 0.5571. It's not so important the numbers, but it's mainly the structure. And if you look at this, I've now decomposed that into what I can call a V sub 1 and a V sub 2. Where V sub 1 is 4 by 2, that 2 being dependent on the number of non-zero singular values, and V sub 2 in this case is actually the same size as V sub 1. Now here's the fun part. Let's look at what actually happens, or now you can answer these equations. If I now take U and multiply it by the transpose of U, what do I get? And you don't have to go through that matrix multiplication. Just remember what U was. I said U is going to be a set of orthonormal vectors. So now I have a set of orthonormal vectors, and I'm going to multiply that set of columns basically by its rows in this product. And if I take the first column of U and I inner product that with the same column, what am I going to get? They're orthonormal, so I now have, let's just say it's E1. What is this? This is, let's call it F's, since this is the output side. So now I say F1 is the first column of U. And if I take the inner product of this, 0.408, 0.408, 0.816 with itself, what should I get if that vector is orthonormal? 1. What if I take the inner product of this first column with the second column? 0. This guy, first column with the third column? 0. Second column with itself? 1. Third column with itself? 1. So now, what does this give me? The identity matrix. And the dimension? How many rows? Well, it's the same as U. That one's easy. And U transpose, U is square. So that's an identity matrix that's 3 by 3. So if I take that U and pre or post multiply it by its transpose, I'm going to get the identity matrix. Because that U matrix is built up of orthonormal columns. What if I take V and hit it on the right? What if I take V transpose and hit it on the right with V? It's identity also, isn't it? And it's now 4 by 4. All right, here's the fun part. Now that we know that, or remembered that, I'm now saying that A is U sigma V transpose, but let me write this in more detail with the U sub 1s and the U sub 2s and the V sub 1s and the V sub 2s and the sigma bar. Now we have a bar. Uh-oh, I lost you, didn't I? Never mind. So now what do we have? We have a U1 and a U2, and we know their dimensions. That has to be compatible with sigma bar 0, 0, 0. And some of those zeros are bigger than just a 0. These may be submatrices. And our V was V1, V2 transpose, wasn't it? That I'm just writing down. But now what if I take and hit on the right-hand side, what if I multiply both sides on the right by V? And remember what I just had here. I said V transpose V was the identity. So if I hit the right-hand side of A with V, and I hit the right-hand side of this right-hand side of the equality with V, I'm going to have V transpose V. That's going to be the identity, and I'm just going to be left with U sigma. But U sigma has special structure if you multiply it out. So let's now look at that. I'm now saying if I now take A and hit it on the right with V, I'm now going to get A, V1, V2. But that's now, if I look at what that does here, I now have U1, U2 times sigma bar 0, 0, 0. But U1 and U2 are partitioned compatibly with that sigma matrix, meaning sigma bar is 2 by 2 and U1 is 3 by 2. So if I multiply U1 times, so if I now do this block matrix multiplication, I have U1 times sigma bar plus U2 times 0. In this rightmost column of that, I have U1 times 0 plus U2 times 0. So that whole right-hand column is going to be 0. Let me write that down. I now am saying that this right-hand side becomes U1 sigma bar plus U sub 2 0. That's now the first column, sub-matrix column. And the other one is now U1 0 plus U sub 2 0. Is that okay? But now, with that, I can actually say that that reduces to U1 sigma bar 0. And what are the dimensions of these? That's still 3 tall, isn't it? But this one, U1 was 3 tall, but how wide is it? U1 was 3 by 2 times a 2 by 2, so it's going to be 2 wide, isn't it? TWO wide, not TOO wide. And how big is this? So now we have to remember how big sigma bar was, don't we? This guy was 2 here, and wasn't he 4 columns wide? The total sigma matrix. This was now 2, bless you, and this was 1, wasn't it? It was a 3 by 4 matrix. So now, how big is this second most set of columns in this product? Or you could go over here and you could say, wait, that has to be the same compatibly with this guy, which is now as a matrix AV1, AV2. Is that clear? But how big is this? That's 2. And what's that saying? If we looked at this result right here, we can see that AV1 is equal to U1 sigma bar. And that's now 3 by 2. Maybe that's not so neat. The neat thing is actually AV2. What's AV2? If we have a couple of vectors in V2 that when multiplied on the right by A gives us the 0 vector, what do we know about those vectors in V sub 2? Where do we call those, or where are they living? In the null space of A, aren't they? So now we have an orthonormal basis for vectors in the null space of A by just construction of this SVD, or this decomposition. Now if we need vectors in the null space of A, we just identify the columns in V sub 2 and we have it. And what are the columns of V1? Well, they're the orthogonal complements to the the columns in V sub 2. So if V2 spans the null space of A, V1 spans the null space, the orthogonal complement to the null space of A, or null space of A per. This guy is the key one. This one says, oh, those columns in V2, they've got to be in the null space of A if all they do is annihilate the columns of A. So this now says that the span of V sub 2 is the null space. And that span, those columns are orthonormal vectors. Those are nice numerically. When you're doing numerical computations and your vectors are orthonormal, that's a good thing. So now we have a basis for the null space of A from this singular value decomposition. And as a consequence, because the matrix, the big matrix V, filled up the entire 4-dimensional space in this example, we now have a basis for the orthogonal complement to the null space of A. The span of V1 is the orthogonal complement of A. I'm sorry, the orthogonal complement of the null space of A. And that's now what I would like to say is a general result. Therefore, in general, U and V, coming from our SVD, meaning here we have A is equal to U sigma V transpose. That's the U and the V that I'm referring to. Those two matrices actually provide orthonormal basis for the 4 fundamental subspaces of a matrix. Meaning if somebody gives you a matrix A and they say, oh, I need to find the range space of A. Well, I can give you a really nice, numerically well-conditioned set of basis vectors for the range space of A. I'm just going to go do SVD in MATLAB. And I'm just going to extract those vectors that live or belong to V sub 1. The range space of A can be then found by, did I say V1? I should have said U1 for the range of A. I don't know. Did you hear me? Just don't play it back. Zero that out if I said the wrong thing. But this is now on the output side, and that's the U in the matrix A, decomposition. If I now said, wait a minute, I actually want to know what's orthogonal to the range space of A. So anything that was in the span of U sub 2, if I now pulled the inner product, computed the inner product of that with A, I better get 0. Because they're orthogonal if I did it in the vectors that are in the range space of A. So there are 2 of my 4 fundamental subspaces. The other ones are, if I look at the null space of A, those are spanned by the columns in V sub 2, the rightmost columns in the vector V, and the null space, or the orthogonal complement to the null space of A, is then spanned by V sub 1. So, if I had the following, now this is going to get kind of crazy because I'm just doing this off the cuff, meaning I'm just making this up as I go. Suppose I gave you a matrix A that was 2 by 4. And I now said, oh, you have one singular value is 2, and the other singular value is 3/2. What do you know about the null space of A? Can you say anything about the null space of A? Can you say anything about its size or its dimension? What's the domain of A in terms of where do the input vectors live in A for that linear map? How big are they dimensionally? What space are they coming from? The input vectors to A. How big do they have to be? If I'm hitting A on the right by a vector to be compatible with A, what dimension does that vector have to be? 4, right? So my domain is R4. And that's the space, that's the dimension of my space for the null space. But now what's the dimension of that null space? I have the sort of the size is 4-dimensional. But now how many vectors are going to be needed to span the null space of A? What's the dimension of the null space of A? It's 2, right? Where did that come from? We know that we have four columns of A, right? And we know the rank of A based on the singular values. We know from this that the rank of A is equal to 2. So we have 2 linearly independent rows and or 2 linearly independent columns in A. Just from knowing the non-zero singular values of A. We can say the rank of A, and we can say how many linearly independent rows we have and how many linearly independent columns we have. If we know we have 2 linearly independent columns, now we start to know how this U sigma V is partitioned. If I said, okay, here is our matrix A, it's now U sigma V transpose. What do I know about sigma structurally? It's 2 by 4, isn't it? And if I put those singular values in, I said it was 2 and 3/2. Shouldn't have made that. Why don't I do it the other way? And then I just fill that up, right? So that now I know that my partition is right there. How big is my U? U2 is basically non-existent, right? I don't have any orthogonal complement to the range space of A in this two-dimensional space. I have a two-dimensional space that A is mapping into, and I have 2 non-zero singular values. I'm spanning all of R2 with this linear map of A. But there is a two-dimensional subspace in its domain in which vectors, if they're living there, will map to the 0 vector. And so now if I looked at this, now I know that V sub 2 is of what dimension? It's kind of confusing, isn't it, with that transpose there? But capital V is of what size? It's 4 by 4, isn't it? And so we know that V2 has to be 4 by 2. So this is now 4 by 2. And the columns of V2 are going to span the null space of A. The reason I created this example is I wanted you to realize, and we could do it just the other way. What if I did the following? What if I said, here's another example. Suppose now we had a matrix B that's 3 by 2, and let's say that its singular values, sigma 1 is 4 and sigma sub 2 is 3. What's the null space of B? What's sigma look like? It's 3 by 2, isn't it? It's going to be 4, 0, 0, 3, 0, 0. What's the null space of B? Do I have a V sub 2 submatrix? I don't, do I? This is telling me what about my matrix B? It has full column rank, doesn't it? So there's no two-dimensional vector. My null space, or my domain, is of what dimension? Or what size? It's a 2 by 1 vector, isn't it? So now each of that, I can't find a two-dimensional vector in R2 that will map to the 0 vector. In this particular B matrix. I have linearly independent columns in B. How many linearly independent rows do I have? What's the rank of B? Just count the number of singular values, right? 2. So that means I have 2 linearly independent columns and 2 linearly independent rows. So there is some redundancy in the rows of B, and that's why now my U can be partitioned as a U1 and a U2. My V is just going to be V1, and I don't have any null space vectors to worry about in this matrix B. So the SVD is very powerful. It gives you a lot of information. You can extract that from looking at the U's, the sigmas, and the V's, but some of these submatrices may or may not exist. In the very first example, I gave you a case where you had all 4 pieces, but you sort of lost rank in both column and rows in that A. But you wouldn't have to for a generic map. We'll pick up with chapter 8 and 9 after the break, and we'll quickly go over generalized eigenvectors, and then we'll move into chapter 10 and hopefully start getting into the infinite dimensional stuff in the functional analysis in the second book. That's the plan. Enjoy your break. I'll see you on Monday.